So what are we talking about today? We are talking about binary search. For the past 2 days, we've been talking about sorting. Now we're going to go into searching algorithms. One of the most popular searching algorithms is binary search. Why is it popular? Because of its runtime, right? Its runtime is log of n, right? So the runtime there is logarithmic, right? Big O log of n is the runtime of binary search. Big O log of n. And again, anytime we see log of n, what comes to mind? What comes to mind when we see log of n? What sort of approach comes to mind? Divide and conquer. Very good. So divide and conquer comes to mind when we hear big O of n. Log of n. Divide and conquer.
And that's because logs breaks it up into...
Exactly. So every time we're looking at that array, we break it up into halves.
Into halves.
Yeah. And the way we break up our array while searching, what does binary search do? Let's start off with what binary search does. Binary search, in the name, it searches for an element in my array, right? It searches for an element in the array. The array must be sorted. So array must be sorted, right? That array must be sorted in order for you to implement binary search on that particular array. And every time we go through the array, we find the middle index. Well, how does it work? How does binary how does it work, right? Array, we said, must be sorted, right? On each pass of searching, or each pass of searching for that element, searching for that value, we have to find the middle index. So find the middle index. We have to find the middle index, and then we split the array in halves using the middle index. Exactly. It's very similar to merge sort in that aspect. But again, the big thing we need to look at here, it uses divide and conquer, as we said here. This is the approach that we're using here. Divide and conquer. So the array must be sorted. It finds the middle index. It splits the array in halves using the middle index. And then it uses recursion to keep looking for the element. That takes us into how awesome binary search is. So if I look at my middle index, I pick at the middle index to see the value at that middle index, right? Based on the value, I will either go to the left array or the right array, right? So if I take a look at that middle value and it's more than my search value, where am I going? Let's just draw an example here. So if I have a sorted array, 5, 7, 11, 15, and 23. We're searching for, let's just keep it simple for now. Let's search for 11. Actually, no, that's too simple. Let's search for 7. So if I'm searching for 7, I split my array up. Everybody with me? Tiffany?
Yes.
I split my array up. Here, let's go ahead and split that array. I split the array in the middle index, correct? I find the middle index here is 11. I split the array up into halves, right? So here I have 5 and 7, here I have 15 and 23. I'm searching for 7, right? Is 11 less than 7? No. So in that case, I am not searching in the right side of the array. Everybody sees that? Right? So I'm looking at my current value. My current value here is 11. That's what I'm looking at. Right? Is 11 equal to 7? No. Right? So that's not correct. So at this point, I am exhausted on the right side of my array. I am not looking here anymore. And obviously here, that's not the value. So that takes us to the left side of the index, of the middle index. Everybody with me so far? Right? So here, 7, I agree, we all agree that 7 needs to be in the left side of that array. Everybody with me so far? Right? So here, we have 5 and 7, so now we are looking here. Well, let's not do red here. Is Eric here? Eric, how you like the colors? Okay. So here we have 5 and 7. That takes us into the place to look for our value right now, right? So already we split our array up into 3 sections or 2 sections based on the middle index. And now we're only looking in the left side of that split. Now we're only looking at those 2 values we have there, 5 and 7, right? So what's the 3 scenarios? The first scenario is the current value, is my middle index equals to that value I'm looking at, right? So let's go ahead and split that array up first, and then we'll continue. So split that array up. We have 5, we have 7. That's what we have left. This is my middle index. Right, because we said 2 divided by 1 is 1. If this is index 0, this is index 1. So far, so good? Yes? Okay, so I look at the current index before I do anything else. Is the current index value equal to our search value? We're searching for 7?
Yes.
Right? Is it equal? Yes, it is. So at that point, I'm done. I just return the index. What am I returning? I'm returning the index I found. Right? And there we're done. So that's binary search. And let's take a look at what linear search is, and then we'll see what the big differences are, right? So this is binary search. If we were to do it using linear search, same numbers, or different numbers, it doesn't really matter. So 5, 7, 11, 15, and 23, okay? Here we have 5 values. Right? Somebody tell us, go ahead and search for 23. Okay? So we're searching for 23 here. Search for 23. If we're using linear search, when we hear linear, what comes to mind? We have to go through each element to find that element we're looking for, correct? Linearly here. So we start off with what index? 0. So we use a for loop, and we go through each index. So is the value I'm looking for, let's go through it. Say we use some index I. Is the value I'm looking for at index I currently? No. I increment. Is it at 7? No. 9, 11, no. 15, no. It's here. It's at 23. So this is the worst case scenario of linear time. I have to go through each element for the element I'm looking for. Here we did not break our array up. We're not saying look on the left or the right based on what the value is. We're not doing any of that. We're going through each element linearly. So already we see if we have 1,000,000 objects, we have to go, worst case scenario, we have to go through each object. So we have to go through each object 1,000,000 times. Everybody with me? Well, not through each object 1,000,000 times, but through our array 1,000,000 times, right? So what does that take us to? That takes us to, what's the runtime of this? If binary search is log n, what's linear search? N, right? So here we're going through our array linearly, right? Through each element. N represents the amount of elements I have here. How many elements do we have here? 5 elements, right? So N represents where we could say N equals 5. So already we see as N grows, we'll take more time to search for that element there. But with binary search, it's way more faster because here, the minute we see an array, it's sorted, we split the array around the middle index. If the value is at the middle index, we're done. If not, we find out, is that value, are we looking for that value in the left array, or are we looking for that value in the right array? And then we go split, we split, we split. At the end of the day, it won't be a million times I'm looking for that particular element, right? It will be log n, okay? Whatever log n, whatever log million is, that will be the answer. It will not be a million times. Everybody with me? Okay, cool. Any questions so far? Yes, sir?
Are there times where, so for example, if the number we're searching for was 5, then this would be faster? Are there times where you're expecting...
That's the best case, right?
Yes.
The best case, 5, we get our number, great. But we're always looking for the worst case scenario.
Are there times where it's better to use linear because you're expecting it to return quicker in like the value set?
I would not. I'll probably use one of, no, I would not use linear. Yeah. Because always, as that input grows, your auto will get slower.
Binary is not limited to like an odd number, right?
No. I could have, we happen to have 5 here, just it demoed better here, but it doesn't really matter. It could be even or odd.
So when you split it,
So if it was 6, if we have an extra number here, say 40, right? What do we have here? We have 6 elements divided by 3, correct? Yes? Eric? Right? So our middle index is 3. It's the same. Where are we here? We here.
why you divided by 3?
We divided by 2. Oh, sorry. What am I doing? I divided by 2. 6 divided by 2 is 3. Sorry about that. Cool. Always divided by 2. Always splitting it up in half.
So if it was 5 divided by 2,
Integer arithmetic. If we say 5 divided by 2 here, what's the answer? 2. It's 2, because we're doing integer arithmetic. Right? We're not doing floating point number arithmetic. Cool? Good answer. Good questions here. Any other questions before we continue to the code part of it? Yes, we always divide by 2. So every time we split that array up, we always divide by 2. So we have 1, 2, 10, 15. We always say how many elements we have here. 4 divided by 2, it's 2. 0, 1, 2, this is my middle element. I split this up, this is 1 and 2, this is 15. I have 2 elements here, 2 divided by 2. I have 1, this is my split, I have 1. Okay? How's yet? Yeah? So always divided by 2 to get the middle index. How do I know to circle the 10? Well, that's index 2 here. 0, 1, 2, 3. This is index 2. When I'm dividing, I'm looking for the middle index. Yeah, the middle index. So if we go back to our notes here, find the middle index, this guy, by dividing by 2. Cool? Any other questions? All right, let's move to the code part of it. Again, we're using the playgrounds here. So new playgrounds, we'll just call it binary search. So what are we doing? We're doing binary search, implemented using recursion. must have array must be sorted. Array is divided in halves to find the middle index based on the value, based on the current value at the middle index, we either continue searching in the left, continue searching to the left of the middle index, or continue searching to the right of the middle index. We use divide and conquer and implement the steps above until we find our value, or do not find value. Steps have been exhausted.
Continue searching for what exactly?
The value. So continue searching for the value, because we're searching for a value. Right, so binary search implementation, what does binary search do? Binary search searches for a particular value. So binary search, we use this searching algorithm to search for a given value. So we use it to search for a given value, and we said the runtime of it is big O log of n. As array is divided on each pass. So here we say it must be sorted, right? So must hello, sir. Cool. So let's go implement it. We'll start off with a function. We'll call it binary search. Again, here we implementing binary search using recursion. We need a given array in our function signature. We need a value that we're searching for. And here we'll have a range of type integer here. And that range is going to be a lower bound range and an upper bound range. Because as we call in our recursive call, we'll be changing that range. Or that range will be changed based on where we are. Are we on the left side or are we on the right side? And even on that right side, are we getting smaller? So the way we get smaller is passing a range in our recursive calls. Very similar to what we did with quicksort, right? Yesterday, we had a low and a high. So here we encapsulate that using a range data type. Okay. We want to check to ensure that the lower bound is lower than the upper bound. Check to ensure that actually the upper bound here is higher than the lower bound. It has to be sorted. It has to be sorted in order for it to work.
I know it has to be sorted, but we're not. I was saying that.
Yeah, we're not. If we have to check for that, we have to go through each array. I mean, through each element to make sure it's sorted. But we're not doing that. We're assuming that it's sorted. Like you in an interview, you assume that it's sorted in order to implement binary search. I mean, yes, you could have your own algorithm to check if the array is sorted, but I would write a helper method for that because if I have it inside of my function, my algorithm will get slower.
The reason why we need it for it to be sorted is because you're checking if the value that's in the middle is greater than or equals or less than what you're looking at. Like the item in the middle, greater than or less than. And then
Okay.
change your
So here we want to make sure that the lower bound, if the lower bound is greater than, if the lower bound is greater than the upper bound, we return nil because at that point, we cannot continue searching because the lower bound cannot be higher than the upper bound, right?
What do you mean?
Oh, we're not returning anything here, sorry. Let me fix this and then I'll continue. So when I'm looking here, basically what this does, it says that if 0, the lower bound, or if 5 is greater than 0, return nil.
5 is in.
We need to ensure that the lower bound is higher than the upper bound. The lower bound is lower than the upper bound, sorry.
And that would be assuming it's not sorted.
That would assume it's not sorted, exactly. So
When you say 5, like, do you mean like the amount in?
the position in the array, or the range I'm looking at. So if I'm looking at an array here, 4, 5, 8, my lower bound would be, lower bound here would be 0, because that's the index 0. Okay? My upper bound would be 2.
So now, how could the lower bound ever be greater than the upper bound?
It's a check. It's a check to make sure that what I'm passing in is correct values. Right? So as I'm passing my values from my recursive call, I want to make sure that I'm checking to see if my lower bound is lower than my upper bound.
As in, if 4 is less than 8, not if.
Exactly.
Ah, okay. So if it's not sorted, 8 and 4 could be switched, and then position 0, 8 is greater than.
There will be different positions there.
Right, yeah, okay, gotcha.
All right. So this is the first check. So that's the first check to ensure that we are correctly working with correct bounds here, because my lower bound needs to be lower than my upper bound. If it's not, I return nil here. If it is, then I'll continue. First, we need to get the middle index. As we did earlier, here we need to do the middle index. So calculate middle index. So here we have middle index we'll say lower bound or range dot lower bound plus upper bound. I keep going directly to upper bound. Range upper bound minus range dot lower bound divided by 2. So that gets us the middle index. Great. So we have 3 checks to do. 3 checks. 1 check, or first check, is it equal to the middle value?
Why is that? Why is it range dot lower bound plus half of?
We have to take the upper bound minus lower bound divided by 2, and we have to add, as we go through each iteration of it, we have to make sure that we keep track of what the lower bound is. If we do not do that, we'll have an overflow error. That's why we do range lower bound here, to keep adding to that upper bound value in order to get the correct value as we go through each iteration.
That was range dot lower bound. which is-
Range dot lower bound, it starts off as being 0,
Okay.
but as we go through different lower bounds, the value will change. The first pass is going to be 0 plus whatever the upper bound is minus the lower bound divided by 2.
And the lower bound is just the index number.
We'll be passing, like we did with quicksort, we'll be passing the first pass, we'll pass the lower bound as being 0, and we'll pass the upper bound as being count minus 1. And then the recursive call will take care of, am I looking to the left side of the index, or am I looking to the right side of the index? And that changes each time we go. So first check is middle index value equal to search key, equal to search key. Let's actually change this value to just search key here. Where we have value, just change this to search so we know search key. That sounds better. So make sure you change your function definition here from search key, from value to search key. So step 1, or check 1, is going to be, is the middle index value equal to the search key? If it is, then we just return, we're done. If it is, we have found the search key. Step 2, if the value at the middle index, what should we do first here? If the value at the middle index is greater, let's do greater, than the search key. If it's greater than the search key, what part of the array are we looking at? Or should we be looking at?
If it's part of the value of.
To the left, right? To the left.
Greater than the search.
The value I'm currently looking at, if it's greater than the search key, I'm not going to the right,
This is gonna be.
I'm going to the left. Okay? So if the value at the middle index is greater than the search key, we will now look at the left side of the middle index. And step 3, if the value at the middle index is less than, Luba, was there a question? I'm hearing Luba and Luba is not here. Oh, okay, you had a question?
No, I was saying that if the value is greater than the middle, that you're looking on the right.
If the value I'm looking at is greater than what I'm searching for, exactly. I know, it's, yeah. Cool, good? All right, so if the value at the middle index is less than the search value, then what are we doing here?
If the value to the middle is less than, then we go to the right.
Okay, awesome. Then we look to the right. Matt, did you have a question? Okay, cool. So those are the 3 checks we do in here. And obviously, if we fail all those checks, we haven't found the value, we return nil. This is why make sure that your function is returning an optional here, because the value might not, or the index might not exist. If the index doesn't exist, we simply return nil, right? So either we have an index or we have nil returned to us. Okay, so let's go ahead and do check 1. Check 1 says if array middle index is equal to our search key, then we return middle index. Right? So if we divided the array, we use that index to see what the value is, and at that point the value equal to what I'm searching for, I'm done. Right? Check 2. We'll say else if array middle index.
It doesn't have to be connected to it? I always thought the else it has to be like.
Oh, you mean like no. It doesn't have you mean like this? Like this here?
Yeah.
Nah, it doesn't have to be connected like this. Cool. So here we separated it up nice for us to see what's going on. So here, if the array middle index, if the value I'm looking at is greater than the search key, what side we're looking at here?
Left side.
The left side. Do we all agree? Right? So I'm currently looking at some value. Say I'm looking for 10, and the value here is greater than 10. I cannot go look in the right side of it. Because again, remember, it's sorted. Right? This only works because it's sorted. Everybody with me? Right? Okay, cool. So here we'll look left side of middle index. And we have check 3. Madame, did I say anything? Check 3. Look at the right side of the middle index. Else here did not find the value. Okay, so let's go ahead and fill out our else statements. So check 1, value equal to current value at middle index, we found it. Step 2, we need to go to the left side. And we're doing everything here recursively, so now we'll actually be calling our recursive calls. So we'll start off by first doing return here, call ourselves, binary search, pass in the array, pass in the same value, search key, and here we need to create a range. Okay? So here we need to create a range. What does that range look like? We'll start off with the lower bound, and we'll go up to not including the middle index. Again, this is very similar to what we did for quicksort. So here, the first time we start, our lower bound example is 0. Right? So this is the left side. I'm not including the middle index. Everybody with me so far? I'm not including the middle index. So this is a recursive call. It's calling a smaller part of the array, or a smaller range of that array. Everybody with me? Right? It gets smaller and smaller until either I find that value or I do not find that value. So this is the left side. Now we'll go on to the right side. So return binary search, pass in the array, pass in the search key, and here we need to construct a range, right? So either the left or the right, we are not including the middle index. Everybody with me? We're excluding the middle index because we've checked for the middle index already. We're not passing the middle value again. So here we want to construct a new range. So we'll say middle index plus 1 up to our range dot upper bound. We don't need that here, do we? Else, actually, let's just do if array, so it reads better. Just update your else statement to an else if statement.
And then the last one would be the else or no?
No. Okay, just to reiterate, so this creates the left side search, right? So range that lower bound up to the middle index, not including the middle index. And on our right side, we were saying middle index plus 1, again, not including the middle index, right? Did we miss anything here?
It's including the lower bound.
Yes, so if I start off with 0, it starts with
The range dot upper bound.
range dot upper bound. This one doesn't have a lower bound here. It doesn't include the upper bound.
It doesn't include it.
Right, it's like the upper bound will be the last element there, but I'm starting from the middle index up to the upper bound. All right, so let's test this out and see if we have any errors here. So let's have a sorted list. 2, 6, 9, 13, 34, 99, and 101. So we have our sorted list. We are getting back an index. We'll call our binary search. We'll pass our array called sorted list. We'll search for, say, 99. And we'll pass in a range here. We'll start off with 0 up to sorted list dot count minus 1. And we'll print what the index is. So print found index. And we'll simply say index, and we'll use nil coalescing and just put in some default value. So if we get back 9 minus 999, that means we did not find what we're looking for. But based on our array here, we should find our value 99, 0, 1, 2, 3, 4, 5. This should be returning index 5 here for us. Everybody with me? Everybody with me? So this should return index 5 based on what we're searching for and based on we're counting from 0. So it returns as the index, not the value. We're searching where's that index for that particular value. Everybody with me? Everybody with me? Any questions?
So we can do this negative number.
Yeah, you could do negative numbers. I could have a negative number here. And we could search for a negative number. Was that your question? Or can I include a negative number in my array?
The range goes from 1.
The range is 0.
No, in
What's that?
the range goes from 1 to range dot upper bound.
We have no 1 in there in our function, you mean?
No, in just 3.
What line number?
Can you go up? In 53.
Oh, this one?
Yeah.
We're saying middle index plus 1, so go to the next index. So if I'm currently at index 3, go to index 4.
It's index.
Cool? Yeah. Good?
Yeah,
It's still sleeping. I need coffee too. We'll get there. All right, cool. So let's give that a shot. So run it.
My computer is acting up. It's not letting me
Do we have an error here? 0, 1, 2, 3, 4, 5. Anybody? Nobody help me here, guys. Oh, I added an extra 1. Okay, I blame Luba. Right? We hard coded 5 in there. Let's not hard code anything. We had earlier we started off with 2, so we were assuming it would be index 5, but we added a new value of -99 that increased our index by 1 because that is if I'm looking for a value that doesn't exist. So if I'm looking for whatever it's 10, right? If I'm looking for 10, 10 is not in that array, correct? It's going to print out -999. Right? It's just a default value. If in case we do not get a value, we get, because we're printing here, the reason why I'm using nil coalescing, we're printing a value. If I do not use nil coalescing here, I'll get a warning saying this is an optional value. Good? Any questions so far? Yes, sir.
So if we were presented like a point where we had to create this function, right? Is it necessary to guard that it is sorted already?
You would ask the interviewer, am I assuming that it's always sorted? The interviewer might tell you yes or no. If they tell you no, I would write a utility function that checks if an array is sorted, and then pass my array to that sorted function. And if it's not sorted, I could either return false, I cannot do a binary search, or then I would sort it using one of our sorting algorithms, right? Maybe merge sort or whatever. Then that becomes a bigger problem you have to solve, right? So at that point, the interviewer needs to say, okay, I know where you're headed. You do not have to implement this function. I understand your logic, right? Then you would say, go ahead and continue. Or he'll tell you, go ahead and implement that function for us to see what it looks like, right? At that point, you would go ahead and implement some function that checks to see if that value I'm looking at is greater than its preceding value. The minute it's not, then it's not sorted. Does that make sense? Yeah. So just having that dialogue with the interviewer there is what you need. Cool? Okay, so any questions so far? Did everybody get their values to, right? So I'll take a look at what's happening here. Okay, so we did it using recursion, right? You could also do it using iteration, which we'll do post-CTA. But for now, we just want to introduce binary search using recursion. There's anything we solve recursively, we could always solve iteratively, right? We've been saying that from when we introduce recursion, right? What does that mean? We use recursion here in our function. Everybody with me? My function calls itself, correct? I could write a while loop that doesn't call the function back, right? That would be iterative. So I'm going through a while loop, I'm checking to see my lower bound, always change my lower bound. Is the value lower? Very similar logic. Everybody with me? Okay? All right, so here, we'll stop here. Or we could make this generic and then stop there. Let's make this generic and then we'll stop here. So let's make this generic. Tiffany, you with me? Okay, so let's make this generic so it works with any comparable value. So my array is generic. I'll convert my binary search to a generic. It needs to be comparable. Why does it need to be comparable? Because we're comparing things, right? We're comparing values here, comparing values. Okay. My array that I passed in. I'm missing an array somewhere. Oh, here, this needs to be type T. The search key, right? The search key cannot be an integer, and my type is generic. Does that make sense? Everybody? Cool. So at this point, we are done, and our function is generic. Let's just run it again. Where am I? Back in our function. So we were searching, our array is of type T, but our search key was an integer, right? That's not going to work, right? So whatever I'm searching for needs to also be of type T. Does that make sense? Because my array is of type T.
But what about the range?
The range is an integer. It's the range is an integer. That's not type T. Yes, exactly. And the return is an index. Yes, we're looking for the index in the array. Okay? And let's test it with a different value here. Let's test it with characters. Again, it needs to be sorted. So we'll say A. Okay, so we have an array here. Let's search character index, and we will call binary search, and we pass in characters. We pass in the key that we're looking for. I'll just say Y. We pass in a range, 0 up to my characters that count, and I'm going to print. And I'll say found character index, and I'll just say character index. And again, here we're just using nil coalescence to just print some value. Here I'll just say -1. Again, -1 here is valid. That could not be an index, right? So any minus value is not a valid index. And now I'll just run it. And we found it at 3, which makes sense, right? So 0, 1, 2, 3. This is where we found Y. Okay. And again, huge benefit over linear search, because linear search would search every element here, right? So it'd go A, is this A, B, C, Y. But with ours, we split the array up, right? Quickly, we see, does Y, are we looking at the left side of the middle index, or are we looking at the right side of the middle index, right? So second iteration, we now have half of the array we're looking at. And in that half of the array, we find it right away, because we split the array again, our middle index is Y. Everybody with me? And the bigger the data set, the more optimizations you'll see there. You have a million records you want to look for, or you want to look through. Linear search definitely is not going to be beneficial there. All right, so now we have our generic type. Anything that conforms to comparable, we could search for, and it has to be sorted. Yes?
You could put dot description dot lowercase, right? If you're searching for one character, because suppose it was like uppercase D or something.
That would be different.
Oh.
Like lowercase a and uppercase a are different.
Oh, okay, so
They're different values, like Unicode values.
then with the closed range between 0 and characters dot count, with characters dot description dot lowercase. Make it maybe over. I did it online.
Okay. You could show me offline, like what's happening there. Okay, so we are good. We'll close this particular lecture. And again, what we did today was binary search. Binary search, the takeaways are, what's the runtime of it? It's log n. Why is it log n? Because it divides my array up every time it's going through a search. Eventually, either I find the value at left or right array, or I do not find the value. Yeah.
Are all of the divided complements log n?
Well, yesterday they were not log n. Those were n log n. Let's go back here, guys. Yesterday, our sorting algorithms were not log n. Please, right? They were n log n. For example, our merge sort, it's n log n because we have that while loop going through our array linearly to make that comparison, right? Our first function breaks it up, log n, but we go into our while loop to do the sorting back into that array, and it has to go through each element. Cool? Same as quicksort. Our quicksort, we went through to create our partition, we have to go through those elements there to always return a new pivot to split the array up again. Cool? All right, very good. So log n is faster than n log n, right? Very good. All right, so we'll stop here.
I love you.